guys want to do? There's momentum. There's a.
Can you solve one where the y, like they give you the radius x equals to a number and y equals to 0, and then they ask you for the rotation about the y-axis. I don't get it why sometimes you don't use the y, you take the x when they ask you about the y.
Which one? Sorry.
It's something like that, but it's MR1, but except they give you like x equals to a number and y equals to 0, and then they ask you for the KE rotation about the y-axis, except you don't use this one. I don't get if they're asking for the y-axis, why you're using the x-axis number.
I still don't understand which one you're talking about. Sorry. I'm gonna pause the video. All right. What questions?
Just solve a problem with impulse.
With what?
A problem with impulse.
Okay, but impulse is kind of straightforward. I mean, we could do it, but let's do it in the context of momentum or something. So, what do you want to do? Inelastic or elastic momentum problem? Elastic? Elastic?
Can we do both?
Yeah, I guess we could do both.
If it's quick enough, like, it doesn't take long.
Yeah. Okay, so a 10 kilogram mass is moving at, let's say, 5 meters per second in the positive x direction, and it collides with a let's say 15 kilogram mass moving at 2 meters per second in the negative x direction. Alright, this is the given. So we can do both of these in the same problem. So if the collision is inelastic, what is the final velocity of the 10 kilogram mass after the collision? All right. Does anyone have an answer first before I show you how to do it? I actually did it. I wrote down something wrong. Hold on. Okay, does anyone have an answer before I show you how? 11? Okay. Anyone else get an answer? Okay, so this is an inelastic collision. So after they collide, they're both moving at some velocity. So, they have the same velocity. The both masses, the 10 kilogram and the 15 kilogram. So the initial momentum of mass 1 would be what? So how do you find the 10 kilogram mass? How do you find its initial momentum? What would that be? Just the momentum of the 10 kilogram one before they collide.
Is it the last one times v1 plus m2 every time?
I mean, just the original momentum of mass 1, right? Or the 10 kilogram one, right? That's how much it has, right? 50 kilogram meters per second, right?
Yeah.
What's the momentum of the 15 kilogram one before they collide? Minus 2, right? You have to take that into account, right? These are vectors, right? So you have to be careful with directions. So it's minus 30. So the original total momentum of both of them is 15 minus 30, which is 20, right? And that's equal to their final momentum, but they're stuck together, so their final momentum is going to be the sum of their masses, because they're essentially one mass of essentially 25 kilograms, like a 25 kilogram mass moving at some velocity, right? So the momentum of that thing would be, after they collide, which is the velocity after they collide, would be 25 kilograms times VF, but that equals what they had before they collide, right? That's conservation of momentum. So this is, what did I say? This was 20, right? So this is positive 20. Oops. I don't know why this computer works weird in this classroom. It scrolls up all the time. But anyhow, this is 25 times VF, so the kilograms cancel out. So it's just 20 divided by 25, right? Basically. What was that?
0.8.
Yeah, right. Yeah, so the numbers work a little bit weird that it's kind of small, but I just made up the numbers at the top of my head. But anyhow, you get 0.8 or 80, whatever you want to say, meters per second, but it's positive, meaning it's going in the positive x direction after they collide. Both of them are going in the positive x direction after they collide. All right, so now you wanted something related to impulse, which isn't that big of a deal, but we can do it. Okay, so what's the impulse of the, what was this? What did I ask? 10 kilogram. 10 kilogram mass before and after the collision. All right, so try to figure that out. Do you have an answer first?
Is it negative 42?
Yes. Should see if anyone else had an answer. Anyhow, the impulse is just it's a vector, but you don't write it as a vector in 1D. Anyhow, it's just the difference in momentum. So it's mvf minus mvi. So it's going to be 10 kilograms times positive 0.8 minus 10 kilograms times VI, but VI was positive, right? It was positive 5, I think, right? So that's it's 8 minus 50, which is negative 42. Right, so it's a vector, meaning it's in the negative x direction. The amount of it is negative 42, 42, but in the negative x direction. Okay, so that's impulse, but you can use this to answer another question. So part C is if the collision took place in 0.2 seconds, let's say do 5 seconds. What is the average force on the 10 kilogram mass? Okay, so try to, so someone already said the answer, but, well, anyhow, so the average force, right, is the change of momentum.
Yeah. Thought about changing time.
Yep. Which is the same thing as the impulse over the change in time. So the average force is just minus 42 divided by 0.25, which is negative 168 newtons, which means it's 168 newtons in the negative x direction. We'll do a whole bunch of parts here because this is good. This should be easy though. Well, see, I'm not going to even pause the video. See if you can answer this. What's the average force on the, what was it, what's the other mass, 5 kilogram? So 15, okay, 15 kilogram mass. All right, this one you don't even have to figure out. Well, I mean, you kind of have to figure it out, but you don't have to calculate it. So what would the average force on the other one be? Without having to calculate it.
Maybe the same.
Almost the same thing.
Well, it have different initial momentum, so it would be a different number.
Would be positive?
Uh-huh. This should be plus 42 when you figure it out. But anyhow, it should be the same number, just positive, right? So, I mean, you can figure it out. So, what was the initial velocity for the other one? 2, right? Negative 2. So it'd be the mass. So it's, what was the final velocity? 0.8, right? It'd be 50 times 0.8 minus 15 times negative 2, right? Because it was going at negative 2. So that's 42, right? Positive 42. And then you divide that by 0.25, and you get the same answer. It's 168. But positive, because it's because momentum always works on Newton's third law, right? That's how basically where you get momentum from, or conservation of momentum, I should say. So that's always true.
I did the calculation, I got 42, but what I don't get is that, like, in another example, another problem, would it always be the same? Would it always be the same number, but reverse, like, instead of negative, it'll be positive?
Yeah, I just went over that. It always works on Newton's third law, right? Conservation of momentum.
So it would not be a different number, you just flip the sign.
Right.
Okay.
Okay.
Do we always just assume that it's just the same number but different sign? Or do we have to do it just to make sure? Or is it always?
Well, I mean, it's a way to check your answer. I mean, it's always should be the opposite sign, but you should also get it from your work, right? If you don't get it from recalculating it, then you've done something wrong. Right? Okay, so this is like 2 steps that you have to do for this one, but it's not too hard. How much total KE is lost in the collision? All right, so try. Does anyone have an answer first before I?
I have 137 on
Okay. Anyone else finish? No? Did you do it?
Formula, like, that I have, like, I don't know what VCM means.
Okay. Let's see how you do it. Okay, so you got to figure out how much kinetic energy they had before they collide. So that is just the kinetic energy of mass 1, which is 1/2, or the 10 kilogram one, right? How fast was it moving?
5.
Oops. So that's 125, I think, because it's 5 squared, which is 25 times 10. Just 250 divided by 2, so it's 125 joules just from the first mass, plus 1/2, 15 times 2, right?
Negative 2.
Well, you're squaring it, so it becomes 4 anyhow. But this is 30, right? Because it's 4 times 15, which is 60 divided by 2, which is 30. Right? Is that right?
Yeah.
30. Yeah, 125, right? And then 1 plus 30, right? So this gives you 155, right? When you add that up. So that's the total kinetic energy for both of them. The first one has 130. The second one is 25. Sorry. First one has 125, second one is 30, gives you 155. And then after they collide, it's essentially one mass, which is 25 kilograms. It's the sum of their masses. 10 plus 5 gives you 25. So it's essentially one mass of 25 kilograms moving at 0.8 meters per second, because that's how fast they're moving after they collide. So that's harder to calculate in your head, but you can do it. It's 8 joules, right? So you went from 155 joules before they collide to 8 joules left after they collide. So the difference in KE is technically it's a negative number because you're losing energy, right? So the final energy is 8. The initial is 155. So it's minus 147 joules, but that means that 147 joules is lost, right? That's what the negative means. So yeah, if I ask how much is lost, it's 147 joules, right? But the point is you always lose kinetic energy in inelastic collisions.
Where did you get the 25 kilograms from?
The sum of their masses, right? They're stuck together.
Wasn't the sum 20? Because
No, 10 plus 15.
oh, that was the velocity.
Yeah. Okay, so all right, so that's inelastic. So let's ask this question. Sorry, if the same masses collided. I don't think collided is a good word, but whatever. Let's just say collided in a perfectly elastic collision. What is the final velocity? Let's use the other mass of the 15 kilogram mass. So it's the same masses, right? But now they're colliding elastically, not inelastically. So let's do that. All right, anyone have an answer for the 15 kilogram mass?
I have 7 in my head.
Okay. Okay. All right, so let's figure it out. Before they collide, it's the same situation as the inelastic case. Before they collide, what was it? It's the same thing, right? As what we did before. What was this part? So this is how much momentum they have before they collide. It's the same thing as what we did in part A or whatever, part A or part B, I don't remember which one. All right, because before they collide, this one's still moving at 5 meters per second, this one's still moving at -2, so it's the same thing as 20 kilogram meters per second before they collide. However, after they collide, they're not stuck together anymore, right? Because it's an elastic collision, not inelastic. So this mass here, I'll call that mass 1, is moving at some velocity, v1f, after they collide. And this mass 2, which I'll call the 15 kilograms, is moving at its own velocity after they collide because they're not stuck together anymore. So there's 2 things you don't know, which is v1f and v2f. Now you can simplify this like we did last time. 20 kilograms, is equal to this thing, right? So this is, the simplified equation for momentum. But the problem is you don't know v1f and v2f, right? So you can't figure out. Essentially, we're trying to find v2f, but you can't find v2f unless you know v1f. So what else do you need to do for elastic collisions? You need to use the equation that conserves kinetic energy, right? Because kinetic energy is conserved in a elastic collision. Does anyone know that equation? It's on your equation sheet. It's this equation, right? v1i plus v1f is equal to v2i plus v2f. So let's put in everything that we know. v1i is plus 5. We do not know v1f. v2i is -2. We do not know v2f. So this is the second equation. This equation is one equation, momentum is the other one. So you have to solve for v2f, which means you want this equation here, the momentum equation, only have V2F in it. So you want to get rid of V1F. You don't want V1F to be in that equation, just V2F. So what we can do is we can solve this equation for V1F. It's not that hard to do. You just add, or sorry, subtract -2. Sorry, not -2. -5 from both sides. I was looking at -2 when I said. And you get something that's not too hard to look at, just -2 minus 5. So that's what happens when you solve the second equation for V1F. So plug into momentum. So the reason I'm doing this is because I want to get rid of it in the momentum equation. So the momentum equation, when you simplify it, is this. And instead of writing V1F, what I'm going to do is write that whole thing. So what you get is 20 kilograms is equal to 10 kilograms times -7 plus, God, all right, plus V2F, right? So you just have to distribute the thing here. 10 times -7 is -70. 10 times V2F is so then, you know, you add 70 to both sides, you get 20 plus 70, which is 90. And on the right-hand side, you have 10 kilograms plus 15 kilograms V2F, which gives you 25 kilograms V2F, and the kilograms cancel out. So you just get meters per second. So basically this is V2F, if you solve for it, which is the thing, it's 20 plus 90, which is 90. Sorry, 20 plus 70, which is 90, divided by 25. So let me make sure that's the answer that I got a second ago. But 90 divided by 25 is 3.6, which is what I got when I first did it. So this is plus Are you kidding? All right, this is plus 3.6. All right, so that's the velocity of the second mass, the 15 kilogram mass, right? After they collide. So it's going at 3.60 meters per second in the positive x direction. While we're at it, let's ask for V1F. Now, V1F is pretty easy to find if you did all the work to find V2F. What is this part? G ready? Right? What's the velocity of the Okay, it's actually shouldn't take too long. But does anyone have an answer first?
I can see the previous.
What was that?
I cannot see the equation where it had the VI.
Well, you can use this one, right? V1F is equal to, one of the steps we did, we wrote V1F is equal to -7 plus V2F, right? So it's pretty straightforward. This is what I was saying. If you figured out what V2F is, which is 3.6, then it's one step to figure out what V1F is. So this is -3.40, meaning that mass 1 is moving at 3.40 meters per second in the negative x direction after they collide. We'll do a couple more parts, just 2 more, and then we'll go on to something else. This pretty much exhausts momentum, though, which is good. All right, one more part is what is the average force acting on the 10 kilogram mass if the collision takes the same time as what we did for the inelastic case. Does anyone have an answer first before I give you the answer?
281 negative 200.
Okay. Anyone else get an answer?
Negative 336.
Okay. And is there a third answer? Okay. So, I guess there's not a third answer. So, you do it the same way that you did it for the inelastic collision. And the average force equation does not change. So basically, it's this equation here. Right? The average force is the change in momentum of the mass that we're talking about, which is, you could say this is maybe mass 1 to get a little bit more specific here. So the final momentum of mass 1 is 10 kilograms times how fast it was moving. Well, times the velocity, I should say. So that's actually negative 34. That's the final momentum. The initial momentum was 10 kilograms, so you have to subtract the final minus the initial, right? That's the delta B. So it's minus the initial momentum, which is 10 kilograms times how fast it was moving before the collision, which was plus 5. So that's 50. But you're subtracting it, right? So it's negative 34 minus 50 gives you negative 84. And then you divide it by 0.25 seconds. Oops. And this would be the average force on mass 1, which is negative 336 exactly, because it's 84 times, well, negative 84 times 4. So it gives you 336. So it's in the negative x direction, but the amount is 336 newtons, right? What's the average force on the other one, on the 15 kilogram mass? Do you think?
Why do you use the 5 meters per second and not the 3.60?
It's the difference in momentum for mass 1, right? So the point is, what would be the average force on the other mass, the 15 kilogram mass?
Oh, positive.
Right, positive 336. All right, one last part, and then we're done with this one, which would be part, what are we on? HI, right? Okay, so what, you could do it either way. But there's two ways to do this problem. It doesn't matter which way you do it. But what is the total kinetic energy after the collision? So I'll probably do it in the opposite way of the way you're going to do it if I had to guess. So I'll show you both ways. You'll probably do it one way, I'll do it another way. Okay, does anyone have the answer? Sorry, I was replying to an email. Does anyone have an answer first?
Are you asking for the energy loss or the
No, the total kinetic energy after the collision.
151.5?
Okay. Okay, so before the collision, it's the same as the case for inelastic, right? Because nothing changes before the collision. After the collision, things change. So you get this answer, right? It's the same thing that we did for the inelastic collision. I mean, the 10 kilogram one is moving at 5 meters per second before it collides, so it has 125 joules of kinetic energy, and then the other one is moving at 2 meters per second, which means there's 30 joules, and you add those two together and you get 155, just like before. So what happens in a perfectly elastic collision if you did everything correctly? To the kinetic energy, that is. So it should be the same. So this should be what you get for after. Now is it? I can just show you. I mean, it's 0.5, right, times, was it 10? How fast was the second? Was 10? Was it 3.6? Plus 0.5 times 15 times how fast the second one was moving. It's negative, but you're squaring it, so it doesn't really matter. 151.5. It's supposed to be the same thing. Hold on a second, hold on a second. Let me look at something. So 20 times 10. Did I write something down wrong somewhere? 20 times 10. Did I write one of the masses down wrong? So this is 10, 10 and 15, right? So that's 20, right?
10 and 15?
No, this first part, 50 minus 30, right? It's 20. What's going on here? V, Y, it's plus 5, right? Minus 2. It's plus 5 minus 2. Minus 7. Put that in there. That's weird. Something is a little bit off. No, it's close. But something is a little bit weird. 25 times 10. Did I write any mass down wrong anywhere? 25.
Oh, I think you put the 3.4 where you were supposed to put 3.6.
Yes, that's right. I switched these. This one I called V1. So this is 3.4 and this is 3.6. I'll go back up and show you why. So that's under 55. Yeah, so the mass, the 10 kilogram one, sorry, the 10 kilogram one is 3.4. The 15 kilogram one, right, that's 3.6. So the 3.6 goes with the 15 and the 3.4 goes with the 10, and you get 155, right? That's what I did. I just switched the velocity. Anyhow, the point is, if you did everything right, you should get the same kinetic energy before and after. So you don't have to recalculate it if you don't want to. In other words, if you already find the initial kinetic energy, it should be the same thing, right? That's the final kinetic energy. All right. Does that make sense? All right. What else do you want to go over? Yeah.
This when they have the forces and then the rotation kinetic about the center.
You mean the torque one?
Yes.
Okay. Yeah, we could do that one. So, all right, I'll just sketch this thing, and then you can, I'll tell you what's going on. All right, so you have a, let's just say it's a disk. So the radius of this thing is, let's make it, I don't know, 0.75. It doesn't really matter. All right, the C value is 1/2, about its center, right? When I write C, it's implied that I mean about the center of the thing. Okay, so let's see. You have one force that's, let's say, applied, say, here, halfway between. This is directly below the center, halfway between the edge and the center. That's where this force is supposed to be. And it goes to the right. So I'm going to say this is force 1. Force 1 is, I don't know, let's make it 20 newtons. Force 2 is directly above the center, on the edge, right? So say directly above it. It's supposed to be directly above it. Oops, at the edge going, let's say down. So it's supposed to be direct. I don't know how close I'm going to get, right? Because when you do the work, it kind of matters that you're, directly above the center, but I don't know how close that is. And, all right, so another force, let's just do 3 forces to make it go slightly quicker. The third force is directly to the left on the edge. It's supposed to be directly to the left on the edge. I'm going to tell you what F2 is in a second. This is F3 going in the positive y direction. So F2 is 10. F3 is, let's make it 5. All right, just to be clear, this is half the radius. Okay. So the question is, just looking at these forces, in other words, you ignore every other force, what is the net torque about the center of the disk? All right, does anyone answer first before I tell you what the answer is? What was that? Anyone have an answer? No? Okay, we'll see. Does anyone else have an answer? Okay, so let's see how you do this. So this is going to get a little bit messy, but let's get rid of this and the radius thing. Okay, so the center is the axis, because that's what I'm saying. What's the net torque about the center? So you have no choice. You have to choose the center to be your axis, which is about there. Okay, so what we need to do is figure out the force, the torque created by force 1. So what's the first thing you need to do when you're figuring out torque given forces, if you're given the force? You draw your line of action, right? And then you draw a line perpendicular that goes from your axis, so it's perpendicular to your line of action, which is this. Well, I didn't want to do that color, but it doesn't matter. And what is that equal to? If I call that's the moment arm, what is that equal to? It's half the radius, right? And what does this force make this? It makes it rotate like that, right, about the center? So that is counterclockwise torque, correct? So it's positive, which I'll write down in a minute, right? What about force 2? What do you have to do to calculate the torque for force 2? Well, you have to do what we did for force 1. So basically, you draw your line of action. All right, so this is, well, anyway, it's supposed to go through the axis, right? I mean, I didn't draw it 100% perfect. But if it, went through the axis as it's supposed to go, then what's the moment arm? There's no moment arm, right? So there's no torque from force 2. And then you have to do the same thing for force 3. So you have to draw your line of action, and that's pretty good. Okay, so this is your line of action for force 3, and then you get to draw a line that goes from your axis, so it's perpendicular to the line of action. What is that equal to?
The radius.
Right? And this makes this go like this, which is clockwise, right?
So it will be negative.
Right. So the net torque, which is the sum of all the torques, torque 1 plus torque 2, but torque 2 is 0, so we don't worry about that one, because the moment arm is 0. So torque 1 is positive, so this is positive F1 L1. And torque 3 was negative, so it's minus F3 L3. So then you just put in the numbers and see what you get. So F1 was 20. So it's 20 times L1, which was 0.75 meters over 2, the radius divided by 2, minus force 3, which was 20, right? 5, times the radius. So I get 3.75, actually positive, right? Because it matters. So the net torque is positive, meaning it's sort of counterclockwise, right? Because the counterclockwise torque was bigger than the clockwise one. Anyhow, the point is you get positive 3.75 Newton meters, right? Yeah.
Can you scroll up? Can you scroll down?
Mm-hmm.
Why was for F1 the L1 was R divided by 2? No. Oh. So is it giving the like to tell you that?
Right. Mm-hmm.
Oh, okay.
Mm-hmm. Right. All right.
Why we use the, or why we have to use the divided by 2 as the radius?
Because that's where the second force, the first force is, sorry, the first one.
It's there, but like, why is it half the radius?
Because that's where it is. It's halfway between.
Yeah, but like how we know, like, is it gonna tell us, like what, if it's halfway or not, so that we know we divided?
Yeah, it was given.
No, it wasn't given, but it's going to be given, like on the test.
It was given. I told you.
Oh, okay,
All right. That good? All right. So the next one is the mass. I'm going to make it small. Let's make it 0.5 kilograms. What is the angular acceleration about the center of the disk? Okay, so no one else got an answer? Okay, what is the net torque equal to? It's on your equation sheet, and we've used it a few times. It's the analog of F equals ma, right, for rotation, which is I alpha is net torque. So alpha, which is the thing we're trying to find, is the net torque divided by the moment of inertia. That's all it is. Now, the moment of inertia for something spinning about the center, God, is C times mr squared. So all you do is take 3.75, which is the reason why you need to find the torque, net torque, and divide it by 0.5, because c is 1/2 times 0.5, so the mass is 0.5, and the radius is 0.75 meters squared, which means the angular acceleration is what was said already, which is 26 point positive, meaning it's clockwise. It's going to make the thing rotate clockwise.
Is that how we differentiate the inertia out of the c and r squared?
No, but it's like something you need to know. Like, in other words, if I give you the c value,
Yeah.
it's the thing, you always multiply by m r squared. That's the moment of inertia. Hold on a second, someone's trying to call me. All right. So, that is the angular acceleration. So, all right, one more part. What is this? Part C. Okay, part C. So, if the disk started at rest after, let's say, 2 seconds, what is the rotational KE about the center? It's probably going to be a big number, but whatever you get, you get. Actually, it might not be that. Anyone have an answer first? No one has an answer? Anyone know how to do it?
No.
I got the equation.
What's the equation?
It's KE rho is equal to 1/2 the L rho squared.
1/2 what? Sorry, one more time.
W rho squared.
W rho. What are you trying to say?
Yeah, I can't use the equation because I don't know what rho is.
There is no rho. But okay, so 1/2.
But the W side, you know that symbol,
Uh-huh.
isn't that called rho?
No, omega.
That's the wrong symbol. Oh, that's for momentum.
1/2 omega squared, right?
Yes, but this time kilometer.
So you need to find omega. So how do you find omega?
Oh.
Which is how fast it's spinning after 2 seconds. You have to use a constant angular acceleration equation, correct? So you need one with omega I in it, alpha and t in it, because you know omega I. What is omega I?
0.
Yes, it starts from rest, so it is 0. We know alpha because that's what we found here. So you take this and you multiply it times 2 seconds, and that will give you your omega, which is, hold on, it is 53.33. So that's how fast it's spinning after 2 seconds, which is another question that can be asked. How fast is it spinning after 2 seconds? But that's not the final answer. So the rotational kinetic energy for this particular the I is c times mr squared, and then you're multiplying it times the omega that you just found squared. So it gets a little bit weird with all these fractions. You have 1/2 from the equation, 1/2 from the c, which is 1/4. But this is what, 1/2 kilogram? times this thing squared, right? You just take this and you square it. So the rotational kinetic energy is 400 actually, exactly 400. Right? So anyhow, this is something else you can figure out, how fast it's spinning, how many rotations it makes after some time using the constant angular acceleration equation. And the other thing you can figure out is the rotational kinetic energy, right? After some time, which is what you do there. All right, so does that make sense? All right, what else?
I get 200. There's supposed to be another 0.5 in there.
Hold on.
Multiplied.
Yeah, like the one that's in
Hold on. Let me double check. So 53.33 squared, right? Times 0.5 times 0.5 times 0.5 times 0.75 squared. Yeah, it's 200, my bad. You're right, 200. I forget a 0.5. 200. Okay. So, what other questions do you guys have? Well, we're reviewing in class tomorrow, too.
So is the one where the circle's already moving, like it's already moving, has some acceleration, there's forces acting on it, and little parts to it. You know what I'm talking about, like that was not on like the homework or the quizzes, it wasn't.
I mean, it's the same thing as what we just did, except it's moving, right?
Is that like different though? That was the same.
It's basically the same thing. Just omega I isn't 0. Everything else is the same.
Can you explain maximum and zero torque?
What was it?
Zero maximum torque.
0 maximum torque?
Yeah.
What do you mean by 0 maximum torque?
It's just like a concept on one of your PowerPoints. It's at 0 and maximum torque, and you like have a circle with like a force. Like, you don't know what I'm talking about.
So, when it's 0 torque?
Yeah.
Yeah, it's when the line of action goes through the axis, right? When its maximum is when it's perpendicular to the axis.
Yeah.
But I mean, that's on video, right? You can just go watch that video again, right? And explain all that in class. But I just explained it again. All right, but like I said, like tomorrow during class, you can ask other questions as well. And I'll put both reviews in the same section.
But like, you ask you questions like you're missing something, but then you know that you're not missing something, or are you missing something or not, like on here?
What was that?
No, what I'm saying is, are you missing something?
Missing what? What do you
Like,
mean?
Another topic to go over.
Oh, topics. Well, what did we do? We did torque. Well, I mean, all the things that we've done. So it's momentum, which we basically finished. Torque, which we did a good, example on. Rotational kinetic energy, which we did. Mode of inertia. Total KE. And constant angular acceleration stuff, right? So we did an example of constant angular acceleration. We did an example of rotational kinetic energy. We did torque. There's a few things we could do tomorrow, like amount of inertia, total kinetic energy, right? We could do that during class, though. Both
So-
classes.
So can you explain, like, on a test, what kind of extra credit it's gonna be with the guitar? Like
Anything can be extra credit from what we did this week or last week, right?
Yeah, but like, can you tell like what specifically might be on the test, like extra
I
credit
can't tell
wise?
you specifically. Give me
Like,
any.
would it be like a conceptual question, at least, like, tell me like what kind of question it would be?
It could be conceptual or calculation.
When you haven't made it yet, or,
No, I mean, I don't know what's on there yet.
or you haven't made it yet?
Let's just say I don't know what's on there. That's a better way to say that.
Okay, like, are you like,
That's enough for me. Thank you.
Okay, see ya.
Bye.
See you tomorrow.
like you can't disclose like if you like are working on it